We owe so much to knots. Thanks to knots, we can tie our shoelaces, we can go sailing, we can tangle our headphones. And when we go climbing, and things like this happen, we can still go climbing the next day. In fact, the DNA in your cells is also all tangled up. And understanding the tangling of the DNA is an active field of research. Let's take a look at the field of knot theory, a field of mathematics with applications in physics, biology, chemistry, and beyond. This is the knot most commonly used for climbing. It's called the figure 8 knot because this bit here looks like an 8. Though, if you're actually climbing, you might see a knot that looks something a little bit more like this if you were to tie it really quickly. But of course, you can tell that these guys are the same by slowly deforming one and then noticing that they look identical. So mathematically, when we talk about knots being the same, we mean they're the same if you can slowly deform one to look like the other. But of course, that leads to a natural problem because this knot is then the same as this knot, which is the same as this knot, which is the same as this knot. And you can see that as I slowly deform this knot, really, the original knot is the same as nothing at all. And so the problem here is the loose end. If you want to study knots mathematically, you need some way to get rid of the end. Mathematicians get around this by only ever considering knots tied on loops of string. Here, I've just taped the two ends of the string together. And this knot is called the unknot because it's not really a knot. Another knot is called the trefoil. This is slightly more complicated than the unknot, and you can see that no matter how I deform it, I can't turn the trefoil into the unknot. Here's another knot. This one here, though, if we play around with it enough, we notice that we can make it look exactly like the trefoil. And so these two knots are indeed the same.
Mathematicians have tabulated many billions of distinct knots and put them into books like this. But how do they know that all the knots in the tables are different? The key is to stop thinking about knots in 3 dimensions and start drawing them on paper.
We can draw a knot on paper simply by tracing out the shape of the knot and taking our pen off the page whenever we want to denote an undercrossing. We can manipulate the knot diagram on paper using one of 3 Reidemeister moves. The Reidemeister moves say that whenever you have a section like this in your knot diagram, you're allowed to replace it with this and keep the knot the same. Similarly, you can replace any section like this and replace it with that. And finally, you can replace any section of your knot diagram that looks like this with a section that looks like that. Now, mathematicians have proven that these are the only 3 moves you need to deform any knot diagram into an equivalent knot diagram. Mathematicians prove that 2 knots are different by showing that they differ in ways that don't change when you apply any of the 3 Reidemeister moves. Let me show you what I mean. Here are 2 knot diagrams corresponding to these 2 knots. A knot is said to be tricolorable if you can color the diagram using 3 colors such that at every vertex, either you only use 1 color on all the 3 strands, or you use all 3 colors. Let's try to tricolor this diagram. If I start with blue here, and then keep going with orange. Now, at this diagram vertex, I have to use green because I've already used the other 2 colors. So I continue with green. And now I've colored the whole diagram, and you see that at every vertex, I've used all 3 colors, and so this diagram is tricolorable. If we try on this one, I start with blue on the top strand. Then I keep going with orange. And now I have to use green on this strand because I've already used the other 2 colors. And now you see that this strand has to be orange because I've already used the 2 colors here. But if it's orange, then it'll clash with this guy, and there'll be 2 orange strands and 1 blue strand. and so this diagram isn't tricolorable. Now you might ask whether or not I could deform this knot in some way so that the diagram that was produced was indeed tricolorable. But that's not possible. If we take a look back at the Reidemeister moves that we looked at before, we see that if this part of the diagram is tricolored before, then you can tricolor it after. And similarly, if this part of the diagram is tricolored before, then you can tricolor it after. And finally, if this diagram is tricolored before, then you can still tricolor it after. What we have shown is that tricolorability is what's called a knot invariant. That means no matter how much you deform the knot, a knot is either always tricolorable or never tricolorable. And so the fact that these two knots have different values for tricolorability, this one is tricolorable, this one isn't, means they can't be the same knot. And we've proven that they're different. So by turning three-dimensional knots into abstractions on paper, mathematicians have developed tools to distinguish knots. Tools like Reidemeister moves, knot invariants like tricolorability, let us answer questions rigorously that our intuition alone can't answer. So next time you tie your shoes, give a moment to appreciate all of the ways that knots impact your life.